there's a survey I remember I got on my desk last semester about feedback from graduate students and undergraduate students, and one of them was they wanted more contact with faculty. Well, look, Professor Eager right here, he is always available. When I took his class back 10 years ago, right about, I was doing some research and I was trying to do electroless nickel on a small nano wire to be able to run an experiment, and I just went to him and he knew all about it, a lot more than everybody else I talked to before talking to him. It happened in the project sometimes. If you work for a company before, or if you have something in your thesis that you're trying to develop, there's nothing wrong with making that your project. You just have to frame it slightly differently, and we are really available to help you. You know, you worked on any design project or something that you had a prototype that was not working. All I can tell you is we deal with those things a lot, and we're happy to provide free advices. It comes with the class. And for me, it's easier if you tell me ahead so we can meet after class or set up a time. And probably the same with Professor Eager. He has an assistant that can take you in the calendar to meet with him. The examples, well, first of all, this is slightly revised, so it does have the fall classes here. It's the same layout that's online in terms of what has been videotaped, except that it has the fall, and I've specified, so I've given material selection in 12 hours as well, but everything else that's on me here is 6 hours. So I tend to be a little bit more to what is needed as the basics in those lectures, especially the one last fall on environmental and mechanical behavior. I talked about corrosion, which a lot of students in the class really liked because it's not something that's taught so much. It's not cool to talk about corrosion, even though it is very important to practicing engineers. And that's an extension of what Professor Eager was saying about nanomaterials and what is taught in class in terms of going to the thermodynamic equation as opposed to how you actually get something done in terms of engineering. And we are trying to bridge that gap a little bit. A lot of it comes from experience. I have to say the first 6 months I worked for a large consulting company, I wasn't very helpful. By the time I had to turn in the assignment, I had spent so much time just learning a lot of practical stuff. And it's not that there's anything wrong with this. I mean, I went through the process like you guys. I did a lot of research. I had a lot of basic skills. I had to learn how to apply it to it was still a very broad consulting structural engineering area, but it probably took me a few years before I was really able to answer questions without having to do a bunch of research on the first place. And we won't be able to take you away from that, but I take that to the extent that some of Professor Eager's examples and stories help you realize that there's things we know, things we don't know. There's nothing to be shy about not knowing. The best way to learn is for someone to teach you, or to spend the time and realize that you need to, get more knowledge, get more data before making a decision on a prototype or anything that you're building. So in terms of work, and that was what I was going to do for overview today, if you are a practicing engineer, so if you're not in a research laboratory, a lot of times you end up having to be involved with a lot of phases of a certain project. Sometimes you, at the very beginning, you have to decide which material we're going to use. You should be thinking about how we're going to put it together. I can't tell you in recent years how many times in the class I had a student come up and say, oh, I'm going to build a pressure vessel out of spring steel. Okay. Now, is your pressure vessels going to be a sphere that somehow you manufacture without any joint? And if that's not the case, you need to think about joining. So, it may look very simple and boring, but there's nothing more important than to think ahead. If you say I'm going to do a cylinder, first of all, you need to think about these corners. They're going to try to flatten out and open. So if you put welds right there, there's going to be a lot of forces, especially if it's welded from the outside on the root of that weld. So a lot of times you want to make this half a sphere, and that way you get away from trying to open up that weld. And maybe you put a lap joint, like these propane tanks that you can buy at Home Depot. But you need to think about it. And if you're thinking about using a spring steel, it limits you, because if you're going to do the fusion welding, you'll learn in the metallurgy class, you're going to have a lot of problem with your strength. No matter what, you'll lose. You can either lose the ductility, you can lose the strength, you will lose both probably most of the time. So you try to put these joints away. And, you know, again, it's just feedback from the class. And you are all smart people, but this came 2 or 3 times over the last year. Just not thinking about all of the material selection process. Just thinking about trying to optimize. Oh, well, I'm going to reduce the strain. I'm going to use aluminum. And you will learn through the welding metallurgy that there are issues in terms of welding aluminum as well. It's not that there are no easy way around it, but in terms of just being an engineer, selection of material goes with joining. And you're lucky this semester there's going to be a lot of joining discussion. Now, I wanted to frame today's overview in terms of this design, failure analysis, and rehabilitation. For design, I picked this project that I worked on most of last year. Different variation, you know. This is a medical device that you do an open heart surgery, and then you form it to a certain shape to put it in contact against the heart on the outside, and then you have a cooling gas that is fed through the inner carrier here, and you have 3. The inner carrier gets split in 3, so you have 3 points here where that gas comes out. It's a liquid and it expands. That creates cooling. So going from, you know, essentially an expansion. You have a lot of pressure on the inside, no pressure on the outside. So there's a return here that is low pressure, and there's a supply that's high pressure. So when you turn on the pressure and you cool it down, it will essentially create ablation on the heart, and then you cool it back up, and then you can move it away. This happened to be a device that is sold, and they have a good fraction of the market, the client that contacted us to work on this. They did want to improve the flexibility, because this is the section that goes, it's a part of the section that goes on top. And what the surgeon wants to do is, he doesn't want to use tools. He wants to be able to do it with his hands. So the risk of forming a kink, and I won't do it on this one. I had plenty of tube, and I'll pass it around, but please don't make too many kinks in it. I have tubes if you wanna go through the formation of kinks. There's a lot of, in that simple device, there is joining. If you look at the manifold over there, there's some barbs to connect. You can see they have a little teeth pattern. The barbs look like this. That's to put a tubing on top. You have to be careful on how you design these if you don't want leaks. There are a lot of different design parameters. This specific connection where the manifold is not in the body, but at the same time, if you're going to go through the process of making your own device like this, any leak, whether it's critical or not, is critical to your reputation. If you connect everything together and then there's some nitrogen gas that starts to come in the operational room, you're in trouble. So when we talk about safety factors, if you can afford it, just make it stronger than it needs to be. It's going to be at low cost for such a small device. When you're in the working zone, so what really goes in the body that you have to bend, if you make it too big, it's too hard to bend. If you, again, make the wall thickness too thin, you're going to form kinks. If you make the OD small, but your wall thickness too high, then you don't have enough space for the gas to flow back. So it tells you a lot about design constraints that you have to deal with. And the bottom line is, yes, you want a metal that is soft. So we're talking about a low yield strength. But you do need hardening, because if you don't have hardening after you bent it the first time, when you try to come again, that's where it forms a kink. And you know, in terms of the application, you just cannot afford it. So there's a lot of practical joining, material selection, and mechanical properties involved at cold temperature. So some of the materials we were looking at, if they had a ductile to brittle transition at cold temperature, just can't use it. This had to go to minus 100 degrees C. So there are a lot of, it's all practical, but at the same time, you need to be able to go from all you've learned from books and try to apply it to us. This one is a very, very specific problem. Another example of recent work is these X-ray sources that are in the scanning systems at the airport. This was another project I was contacted because they had trouble. So you have the whole scanning system. You need X-rays. And this device here essentially produces the X-ray for you. It works a little bit like an electron microscope, if you've seen an SEM before, where you start with electrons, you energize them. So the electrons come from that filament here, and they hit the surface, they produce X-rays. And that's what you use to shine on the luggages, and you have detectors on the other side to find out what's going on. So the main objective for these people was trying to get as many X-rays as possible for a low cost. It turns out that the sources of X-ray were a lot cheaper than the detectors. So one of the technologies to improve the scanning systems is to have multiple sources scanning on a single detector. If the detector is 5 times more expensive, and I can sequence it fast enough, if I'm at 600 hertz, for example, in changing from which source the X-rays are coming from, I gain a lot more information about the luggage than if I try to match one source and one detector. The main implication of this is at 600 hertz, this electron current was turning on and off. And I had to tell them, well, maybe you just want to just block it here. So you still have your source running in steady state, and you don't have to worry about fatigue. This was a fatigue issue from the idea of switching the current. The response I had on that is, well, I'm going to need more power supplies. I'm going to need a lot more current. I mean, the whole idea is you have one power supply and you flip it among different sources. And first of all, you don't need to go to a 220 volt or a 480 volt unit. But also in terms of hardware, it's less expensive to put together. So all these practical limitations essentially tell you that this had to be very hot and cool off at the same frequency of turning it on and off. And that's essentially what we worked on, doing the thermomechanical analysis and trying to figure out materials that would resist potentially higher temperature or higher temperature variations from turning it on and off. So the system, again, you shine here, it's a tungsten type disc. There was a lot of proprietary information that they didn't even tell me about how they made it, but we had to characterize it to the extent we could to know if it will crack or not when it goes through these thermal cycles. So it's just a practical example. It has nothing to do with, in our class, you'll hear a lot about trouble people have. They were sort of okay. They didn't have the life they wanted because eventually they had, and I think I have an image of that. This is the thermal profile on the source, and they had cracks forming on these little tungsten discs where the electrons were coming in. And some of the cracks were transverse, like the ones that are shown here, which may or may not be a problem. If you start with a flat surface and you break it down a little bit in smaller pieces, you can still use it as a source. One of the problems is some of the cracks were bifurcating, and then you lost your thermal conductivity, and you started almost melting the tungsten on the surface because it didn't have the heat pattern to go from tungsten to some form of a copper to a cooling fluid. So this idea of the cracks turning on them was, one of the big issues. And it's not uncommon for materials to have a lower resistance to cracking in the rolling plane, if you will, in the plane where it's formed, because the inclusions get flattened up, and you essentially have pads that of low bonding energy, where you can, if the crack's coming down and it hits a bunch of precipitate or inclusion, it will turn if there are also shear stresses from all that thermal gradient that allows for that to happen. The World Trade Center is something Professor Eager wrote a very nice paper on. I decided to bring it up just to show a little bit sometimes that there's something to be learned from doing this failure analysis. It was a terrible catastrophe, and there's nothing to be do about it. I mean, the building is gone, the people died or were injured, and it's the end of it. There won't be another World Trade Center, although, is it completely up, the Liberty Tower, or are they still working on it? Yeah. Yeah. I worked on the foundation welding. They had issues. It's going to be strong, but when you oversize your design, there are things that normally are not any issues that now all of a sudden you have to worry about it. You put more braces, and now they meet with each other. You have a more external expansion trouble if you have redundancy in your system. There's a lot of issues. Anyway, regarding the World Trade Center, one of the issues that came up from looking at some of these photographs, and this is not just my theory. There were a lot of people that have worked on this. And believe it or not, I don't really mind. But from the heat that was localized in a certain area, one of the theory is the wall of the building caved in. And the reason why some people say it caved in is these floor or trusses or joists that, first of all, are very thin metal. They're holding a lot of dead weight, and therefore they will heat up very quickly and sag. So if you have a truss that starts to sag, it pulls on the main columns. It's one of the theories. Now, what does it mean? Well, if you wanted to gain 10, 15 minutes of life on this whole tower, insulate these floor trusses or make them such that they'll come apart and you lose one floor or something, but the whole building, the main columns won't come and starts to buckle, essentially. So it's this idea that, yeah, you want to insulate the metal, and probably you want to insulate the main columns. But if at the end of the day, what ended up being the trigger is this pulling action to create the buckle, then you need to prevent that either by not using steel. You could use concrete, pre-stressed concrete for your floor support, or insulate it or make it such that it will disconnect when it reaches a certain temperature or a certain capacity without creating too much pulling action. So that's, I guess, my one example. If you're going home tonight and say, why these guys do failure analysis? It is just to fight over who made the mistake and that kind of things, and not always. Sometimes it is, sometimes there are lessons to be learned for future design. They changed a lot the fire protection building code based on these studies. Now, blowout preventer, we're not going to have time. I will talk to you guys about blowout preventers. I actually brought a piece right here, and maybe we could do it. I was lucky enough to work on the big spill, the BP. This is a very simple packer system, and what you do, and I'll show in a video, It's a little heavy, but it can be turned around. What happens with these systems is you want to be able to shut the well when there's a drill string in the hole. And there are multiple ways to do that. One of them is to use sort of a donut that will come out of the housing of the well, and press all around against the tubing. Or you can come with two C-shape, which is the design that I'm circulating right now. And it's just a little awesome. I just let it go. It starts over. So this is the whole casing diameter, if you will. So this goes up and down, and what happens is you have the drilling mud or your production coming through that tubing that's inside the well. And this, you're talking about something that's 3/4 of an inch thick, as much as 3/4 of an inch, maybe 3/8 in general. So one of the things that happened with the BP spill is they had some knives to try to get that pipe out of the way, but it wasn't sharp enough at the right location, so they were not able to completely go through that drill string. But you can see that as being a challenge if what you want, it's a valve, okay? But if you want a valve to resist 10,000 psi pressure, which is about 100 times what you have or more, what you have in house plumbing, you need a lot of metal to hold the rubber. So if you look at this here, what we're working on is making a rubber seal between the packer, it's the piece that you have, and the drill string right here. And you also need to make a rubber seal against the cavity around it. It's really not an easy process if there's flow in the well. If you have drilling mud that has all the little particles from drilling, it's very, very abrasive. So there's no doubt that it's a challenging environment to be designing something. At the same time, it is important. If people call it a blowout preventer, they expect that when there's some pressure rise in the well, they'll be able to seal it. It's an example that involves a lot of environmental factor. You can have H2S in some of these wells. So if you have steel, you have to be careful about residual stresses, hardness level. If you have rubber, the rubber also will deteriorate under certain gas environments. So there's a lot of material selection, wear, and just basic design that is involved in this. Now, exactly what was learned, because that's another example of failure analysis, I think a lot of people did learn to some extent that they needed to make not consider these foolproof because they didn't work all the time. So whether they're going to change regulation or whether it still becomes a responsibility of the designer to make these reliable is still an open question, I think, even 2 or 3 years down the road. Because there are some specifications on how to make these, but they're not very detailed. It's a little bit like in automotive. Here's, you put the light, and you need to absorb a certain energy if you have an impact, and the rest, good luck to you. There are some performance requirements. They don't necessarily encompass all the conditions that will happen. So that will be it for today. And tomorrow, Professor Eger will start on the welding metallurgy, and I will continue Thursday. And I have this list here about when you make the decision you're going to use structural material, it's more than just putting it on the drawing. So that's what I'm going to talk about on Thursday. It's here.